Hi everyone, welcome to Vedantu English. I'm Diksha Kaushal, your chemistry master teacher. So everybody do let me know if I'm clearly visible and audible to all of you or not, and let me see why the students have not joined. Let us wait for the students to join in so that we can start with today's session. And today we are going to do chemical equilibrium. So chemical equilibrium, guys, I have divided into two parts, right? First is this all about like basics, law of mass section, what is Kp, what is Kc, and you will see, right, that in chemical it's quite a simple chapter, right? Definitely not to be skipped for your JEE mains. Some students think, this chapter it's so simple, I'll easily do it. But when you lose marks in one of the simple chapter, then it hurts a lot, right? So definitely you should not skip this chapter. What you can do for this chapter is do the highlight important things for this chapter, and that I'm going to discuss in today's and tomorrow's lecture. So guys, do let me know if I'm clearly audible and visible. Chandu, Shrishti, Avakti, Santosh, Krik, yes. Let me know. Shall I start with the class, everybody? If the sign is yes, then we shall start with the class, everybody. Let me just inform the students in the on the Telegram group that we are live in the class, right? Um, okay. So, first thing first, let's understand what is equilibrium. To understand that, firstly, we need to understand one thing, the types of chemical reactions that you have. So you majorly have two kind of chemical reactions, and ma'am, we have also discussed this in thermodynamics, yes. But in thermodynamics, we discuss about the work thing of reversible and irreversible processes. Here we are just completely going to see that what kind of reactions will show equilibrium, reversible or irreversible. So irreversible reactions are those which will only move in one direction, they are not moving backward, so they are only in the forward direction, right? These are irreversible. But reversible processes which move in forward as well as backward direction, that is reversible process. Reactants are almost completely consumed here and converted to product. But in this case, as the reactant gets converted to product, it will again come back and get converted to reactant. So there is no completion in this reaction. So never completely converted into products, right? They do not attain equilibrium. Why? Because for equilibrium state, forward and backward reaction should be same, and that is the reason they do not attain equilibrium. But equilibrium is only achieved by reversible processes, right? So one thing you can write here, that only the reversible processes, for example this process, that is H2I2, Haber's process N2NH2, then thermal decomposition reaction of, but thermal decomposition reaction in a closed vessel. Because if the vessel is open, then the products that are formed will be in the surroundings, and that is the reason in the open vessel the thermal decomposition reactions are irreversible, and that's why in the open vessel no equilibrium will be achieved. In the closed vessel you will see that equilibrium is achieved, right? Okay, yes everybody. So yes, Beta, you are asking me to explain in Hindi, but the name of the channel is Vedantu JEE English, right? So this channel is where we will teach you in English, so that every single student, right, can learn this without any regional language barrier, right? That is why this particular channel was made, right? That was the whole point of teaching in English, right? So irreversible process reactions in the open vessel, these are irreversible. and the reaction in the closed vessel are reversible. Okay, these are all the examples. Now, if you see, equilibrium is only possible in the reversible processes. In the irreversible processes, equilibrium is not possible only. So, all the reactions that you will see in equilibrium are showing reversible process. Okay, all the processes, guys, that you have here will be reversible. Irreversible processes never going to show you any kind of equilibrium. But ma'am, what is this equilibrium? Let's understand that. Okay, so equilibrium represents the state of a system in which properties like pressure, temperature, concentration do not change with time. These properties with time, they are not changing. That means I can say one thing, that these things, especially I'll write concentration because we'll talk about concentration only here, and we'll also talk about pressure, right? So that's why I'll be writing these two things here, and obviously temperature also, but I'm writing these two things, right? Or you can write this as well, right? They do not change, that means they are constant, right? I am not saying it should be same. I am not showing, obviously temperature will be same in forward and backward. Temperature of the atmosphere is one only, right? That's why I'll be writing concentration and pressure here. If you talk about concentration of reactants and products, I am nowhere saying that if you have a reaction A plus B give rise to C, then all of them should have same equilibrium concentration or same equilibrium pressure. I am not saying that. I am saying at equilibrium, concentration and the pressure will be constant, not same. Okay, so remember that it will be constant, but I am nowhere saying that it will be same, right? But if I talk about the rate involved here, that is very important. Rate of the reaction of forward. Forward means to make products. For example, you have a reaction that is R2P. Now R is the reactant, P is the product. And when you are going in the forward direction, that is rate of forward direction. And when you are going in the backward direction, that is rate of backward direction. So we are saying that at equilibrium, the rate of forward and the rate of backward is same. That means in the same speed. For example, you are running somewhere, okay, and you are running forward and backward. Let's say you are running in the forward direction, your friend is running in the backward direction, right? Not like that, but what we can say is, okay, let's take an example. For example, I have 10 balls and you also have 10 balls. I have 10 blue balls, you have 10 yellow balls, okay? So what we are doing is, if my speed is faster than you, I am throwing two balls at a time. You are only throwing one ball at a time. So definitely there will be no time where we both will have equal number of balls, right? That will not be there. But if I am throwing one blue ball at you, you are throwing one yellow ball at me. So always what will happen, because the rate of throwing of Diksha ma'am and the rate of throwing of, let's say, Dhanush is same, right? Our rate is same, and that is the reason that always and always you and me both will have the same number of balls. The color may differ, but same number of balls will be there. So that means rate of forward and backward direction is same, right? So this is what we want, that rate should be constant and same. Rate is constant also, rate is not changing, and rate is also same. That means at equilibrium, rate of forward direction is equals to rate of backward direction. This is quite an important thing to understand. Okay, everybody, right? Okay. Now see one thing. Okay, ma'am, rate of forward direction and backward direction is same. That means, ma'am, you are saying that nothing will change. Means this is in a static condition. No, it is not static. Actually, it is in the dynamic equilibrium. Ma'am, what is dynamic equilibrium? What do you mean by dynamic? Tell me. Everybody in the chat box, let me know what is dynamic. Ma'am, have you completed thermodynamics? Yes, we have done thermodynamics, right? You can go and watch the lectures, we have already completed it in detail, right? Now, dynamic means change. That means when I am throwing balls at you, you are throwing balls at me, our rate is same. It's not like I'm standing like this. Let's say you also have blue balls, I also have blue balls. I am throwing one ball at you, you are throwing one ball at me. Now, to for some other person who is not seeing that we are actually exchanging the balls, because the color of the ball is same, right? That is the reason, to the external source, he only can see that Dikshanam also has only 10 balls, and this person, let's say, who is this person? Let's say Lokesh. Okay, Lokesh also has 10 balls. That means we can say that this is dynamic. We are exchanging the number of balls, right? But the rate is same. That's why overall in the picture there is no change, right? So when overall in the picture is not changed, that is equilibrium, but it is definitely changing. So if I talk about one more example here, that for example, there is a tap, and this is the bucket, and this is also one more hole over here, right? In this bucket, you can see the water is flowing from this direction and the water is coming out of this hole. So what is happening? The rate at which this is flowing and the rate at which this is going, right? The rate at which this is coming in the bucket and the rate at which it is going is same. If let's say the rate is different, here the flow is greater. Let's say the rate of throw, it's let's not write it, let's write it as rate of flowing. Let's say rate of going, right? Rate of RC and RG. Okay, if RC is greater than RG, then what will happen? If this water is coming here, but this is at a faster speed, but this is going away at a slower speed, then the bucket will be filled, will be filled. Though slowly, but the water in the bucket will increase here. What if I say that RC is less than RG? That means this is RC, this is RG. Tell me, the bucket, the water in the bucket will be decreased or increased? What will happen here? If here the rate at which the water is coming in the bucket is very slow, but the water that is coming out of the bucket is very large. It's like your mom is giving you sambar, right? She is giving you one sambar, you're eating it. You more sambar, you're eating it. The rate at which sambar is coming in your plate is so less as compared to it is going into your stomach, right? So the bowl will be empty, right? Why? Because you're eating at such a faster pace, right? So here, when it is going out of this, right, that means this is going to decrease. So it is not at equilibrium, the concentration is changing. But if I say the rate of water coming and the rate of water going out of the bucket, right, if this is same, then I can say that always this concentration will remain the same. There will be no change in the water level of this bucket, because the rate at which it is coming and it is going is same. So this is dynamic equilibrium. So equilibrium is not static, equilibrium is dynamic in nature, right? This is another example of that. A tug of war in which two sides pull, right, equal forces, right? That is also a case of equilibrium, right? But that is a case of static equilibrium, because no one is changing. I am pulling you, you are pulling me. We are not changing. We are at the same position. So that is static. Here it is changing. This is called as dynamic, because water is coming, water is going. That is dynamic equilibrium. Okay. Yes, everybody. Now let's see the types of equilibrium that you have, right? Two classes. Today one class, tomorrow one class. Okay. Next is solid liquid equilibrium. So for any pure substance at atmospheric pressure, the temperature at which solid and liquid phases are at equilibrium. Let's say the ice and liquid, when they are at equilibrium, right? At equilibrium is called as normal melting point, and the temperature at which they are at equilibrium is called a normal melting point or normal freezing point of the substance. For example, water as solid and water as liquid and the temperature at which it is at equilibrium is called as normal melting or normal freezing point, right? Then liquid vapor, when the liquid and the vapor state are at equilibrium, this is at liquid and this is in vapor state, right? That is at equilibrium. And here the temperature at which they are at equilibrium is called as normal boiling point of the equilibrium. And boiling point depends upon the atmospheric pressure, therefore it decreases at higher altitude. This we have seen in solution chapters, and those students who are of class 11th thinking, ma'am, what you just said. Wait. See, the definition of boiling point is that vapor pressure should be equals to atmospheric pressure. So if atmospheric pressure changes, boiling point will change. And if still you are not able to understand this vapor pressure and all, that we will study in class 12 solution chapter, right? And those who are class 12 students, they already know what I am talking about, right? Next is solid vapor. When solid and gas, they are in the equilibrium state, that is called as solid vapor equilibrium. Now let's see dissolution of solids in liquid, right? When the solids get dissolved in the liquid, let's see this. This is also another kind of equilibrium that you have. If you see, there is water, right? Water, water, water. And you have added which thing? You have added sugar into it. Let's say we have red color of sugar that is being dissolved. Okay, red color is of the sugar that is being dissolved. Okay, this is the dissolved sugar that you have. Now when you add sugar, sugar is being dissolved. At one point, sugar be like, water be like, I can't dissolve more of sugar into myself. I am done with this much sugar. And to you are like, this happens now when you can't dissolve in one glass of water, you can't dissolve 10 spoons of sugar, right? There is some point at which only, if I say you can't study for 20 hours in a day, right? Then you also have a saturation point. So they also have a saturation point. Water also can dissolve some amount of specific amount of solute into it. So when its saturation point is achieved, when it is now a saturated solution that I will not dissolve more amount of solute, then there will be the case of equilibrium. When you add more of sugar into it, let's say more sugar particles I am mentioning by pink. So when you dissolve more sugar particles here, as one sugar particle you add here, right? Let's say one sugar particle, one extra you have added, this will get dissolved, right? This will get dissolved, this will get dissolved, and some other sugar particle, already dissolved sugar particle, will get undissolved. Then you add one more sugar particle, this will get dissolved. That means this is a rate of dissolution. And some other already dissolved sugar particle will get undissolved. And to you are happy, you are like, oh, 2 sugar crystals I have added, they did not get dissolved. That means it has stopped dissolving the sugar. But actually, it has not stopped dissolving the sugar. It's not like it has stopped dissolving the sugar. The rate of dissolution of sugar, the rate at which the dissolution of sugar takes place is equals to rate of crystallization at which already dissolved sugar is being crystalled out as sugar, right? So as I can show you one more thing, you add one more particle here, you add one more particle here, right? You add one more particle here, right? Now this particle will be dissolved, right? This particle will be dissolved, and what you will see is some already dissolved sugar particle will get undissolved. Okay, so total 3 you added, 3 are undissolved, right? But actually it is existing in the equilibrium state. Then guys, next is gases in liquid, that is your Henry's law. So gases in liquid also have this in detail. We'll discuss this in solution chapter in class 12th. But gases in liquid has a thing that it states that mass of a gas dissolved in a given mass of solvent at any temperature is proportional to pressure of the gas. More pressure you apply, more solubility will be there, more it will be soluble. Now this we will study in solution chapter. Okay, in chapter, in class 12th, where gases are being dissolved, because they also are in chemical equilibrium, physical equilibrium with each other, right? Now let's talk about chemical equilibrium. That is the name of this chapter, chemical equilibrium. As I told you, chemical equilibrium will exist for reversible reactions, right? Taking place in the closed vessel. Always it should be in the closed vessel. Now what will happen? At first, rate of forward reaction will be greater than rate of backward reaction. Tell me, when the rate of forward reaction is greater than backward reaction, let's say you have a reaction. This is a chemical equilibrium where the phases are not changing, the states are not changing. It is getting converted to a new chemical itself. That is chemical equilibrium. So in this case, reactant is being converted to product. If I say forward reaction is very high, that means the product formation is favorable here, right? It is in the forward direction. Only reactants, we can say rate of forward reaction is greater than this. Yes. Initially, what will happen, because you don't have any product here, so reactant will start consuming. There will be no backward reaction. And in the second step, when you have some amount of reactant, that is some amount of reactant that is converted to product, you have some product also. Now rate of forward reaction decreases and the rate of backward will increase. Now forward, when some amount of product is formed, now what will happen? Instead of only one direction, it will also move in the backward direction. So what will happen? Forward and backward both will be there. And there will be a point which is at equilibrium where rate of forward and backward reaction will be same, and that is the point of equilibrium, and that is called as chemical equilibrium, right? So the stage when the rate of forward reaction becomes equals to rate of backward reaction, right, that is called as equilibrium. Concentration of the reactant and product becomes same. Okay, right everybody? Now see this thing, graphical representation of equilibrium state. If you see this here, this is R1 and R2. These are the reactants, these are the products. Now can you see this one thing over here? Actually, I would like to teach you, yes, there are all the graphs here. This is very important thing, guys. This is very important. Firstly, we are discussing about forward and backward reaction rate. I am saying that as the reaction proceeds, rate of backward reaction increases. Rate of backward reaction increases, rate of forward reaction decreases till rate of forward is equals to rate of backward. Because see, three steps we discussed. We discussed that initially you will have only rate of forward reaction, right? A rate of backward reaction will not exist. Then rate of forward reaction will start decreasing, rate of backward reaction will start increasing till at equilibrium rate of forward and backward reaction become equal. And this is, now we will show this in terms of graphical representation. This is rate, this is time. Backward is increasing, forward is decreasing. Equilibrium state will be that state where both of them are equal. So is this a graph of equilibrium? Definitely yes, this is a graph of equilibrium. What about this one? What about this one? Right? What about this one? I'll draw one more graph here. If I say one thing, if I, instead of drawing this graph, if I draw this graph, if I draw this graph where this is forward, this is backward, tell me, then will it be equal or not? Tell me. Then this is a state of equilibrium or not? Now this is rate of forward, this is rate of backward. They are becoming constant, but they are not same. So this is not a graph of equilibrium. Okay? This is not a graph of equilibrium, right? If I draw another graph that looks like this, If I draw another graph, now you will tell me whether that will be equilibrium or not. Now you will tell me whether that will be equilibrium or not. You have a forward direction, you have backward graph that goes like this. Okay, this is rate of forward, this is rate of backward. Is this a graph of equilibrium or not? Can you say this is a graph of equilibrium? Yes. Yes, tell me. Is this a graph of equilibrium or not? Can you say? Rate of backward is not equals to rate of forward. Then how can you say this is a graph of equilibrium? Definitely not. This is not a graph of equilibrium. So when you draw the graph of rate versus time, then forward and backward should be same. Only then we will say this is forward, this is backward. If rate of forward is equals to backward, only then we will say equilibrium has achieved. Otherwise, it has not achieved. But if I say concentration versus time, now concentration, I told you it should be constant. Nobody is saying it should be same. Concentration, I am not saying it should be same. No, concentration has to be same. No, concentration just has to be constant. So if you see this here, concentration is constant. So this is definitely the correct graph. Here, this is the stage of equilibrium when the concentration is becoming constant. The concentration is not changing at equilibrium, right? Ma'am, but here concentration is same. So concentration can be, concentration should be constant. It can be same, it cannot be same, right? It can be same, it cannot be same. So this is also the correct graph. What about this one? Is this the correct graph or not? Concentration of reactant is decreasing, product is increasing. Is this a graph of equilibrium or not? Tell me. Yes, definitely, Lokesh. After this, it's the time of ionic equilibrium only. But ionic equilibrium, the base is chemical equilibrium, right? So after this, I'll start with ionic equilibrium. Ionic equilibrium will take 3 to 4 classes. It's a big chapter. Okay? Yes? Yes, ma'am. This is also a graph of chemical equilibrium. Because the concentration are constant, it may or may not be same. How does it matter? Right? Now let's see. Based on this very simple thing, they have asked you a question in JEE 2020, that is for the equilibrium A to B, the variation of rate of forward and backward, that is reverse reaction with the time is given by which thing? Yes, everybody, tell me in the chat box, that will be given by which thing? They are saying variation of rate of forward. Rate should be there. This is rate. A is the rate. B is the rate. So tell me, everybody, spam it in the chat box, everybody, and do hit the like button. What you guys are doing, huh? So less likes are there, students are more, and that is quite disappointing. So hit the like button, everybody, and answer me in the comment section, in the chat box, what is the correct answer over here? Is it 1, 2, 3, or 4? Where you can see the rate of forward and backward is same. Where the rate is same, only over here the rate is same. Others rate is not same. So answer will be 3 is the option number 3 is the correct answer. Rate of forward reaction is equals to rate of backward reaction, and this is the correct graph here. So answer is going to be 3 is the correct answer here, right? Okay. Yes, everybody. Very good. Now let's talk about the characteristics here. Easy peasy, yes, and still very few students have answered. Let's see the next one. Next is characteristics of chemical equilibrium, right? What are the characteristics? First, we are saying that always it happens in a closed container. There should be a closed container. Only then the products will not escape into the surrounding, right? Equilibrium can be established from any direction you take, right? From any direction, equilibrium can be established. from the forward direction as well, from the backward direction as well, right? So even if you say, now this particular reaction is for when you have N2 plus H2. Now concentration of NH3 is increasing, no? So it will be this reaction. Here concentration of NH3 is decreasing. In this case it is forward, and in this case NH3 is decreasing, N2 and H2 is increasing. So this is the backward, this is the forward, this is the backward, or you can also write it like this. N2 plus H2. I am not balancing the equation over here because I am just telling you that what is going on here. So it is the backward, it is from the backward direction, this is from the forward direction. Equilibrium you can achieve from anywhere. Because Louis, if you have open vessel, you have the formation of any gaseous compound like ammonia, it will escape into the atmosphere. Then how will it will show backward direction? It is already escaped into the atmosphere, right? That is the reason. Next is, it is dynamic in nature. Equilibrium is quite dynamic in nature. I have told you what is dynamic. It is means overall it is changing, but the change is same. That's why net effect is zero, right? So no net change is there. Equilibrium, both reactants and products are present and the concentration do not change with time. That we have seen that concentration are same, concentration do not change. Equilibrium can be observed constantly of some observable properties like color, pressure. Now we are saying that in equilibrium, what all things will be constant? Pressure will be constant. First thing we are saying is pressure will be constant, color, pressure, concentration, density, temperature, all these things will be constant at equilibrium because there is no net change at equilibrium, right? A catalyst can alter the rate of approach of equilibrium but does not change the state of equilibrium. Now this is an important point, that if you talk about a catalyst, this we will see in class 12 chemical kinetics, the full-fledged reason, like full-fledged function of a catalyst, what it does. But as of equilibrium, what you need to remember, that a catalyst will not change the equilibrium state. It only makes a reaction fast by changing the activation energy, by decreasing the activation energy, that you will see in chemical kinetics in class 12th, right? Okay, so as of now, just remember that here catalyst will not alter the equilibrium state. It will do nothing. Can alter the rate of approach of equilibrium but does not change the state of equilibrium, is not changed because of catalyst here, right? Then at equilibrium, Gibbs free enthalpy is zero, right? This we have seen even in thermodynamics, that at equilibrium delta G was equals to zero. Equilibrium state can be affected by alternating. Now this is basically Lee-Chatelier's principle that we are going to discuss in the next class. Okay, tomorrow we'll discuss Lee-Chatelier's principle in detail, right? Lee-Chatelier's principle we'll discuss in detail. What if negative catalyst? Then it will slow down the rate of reaction, right? Okay, yes. Usually we talk about positive catalyst, but there are negative catalysts also that are used, right? Now let's see law of mass action. Yes, everybody, let's understand law of, should I learn isomerism to watch this lecture, ma'am? No, isomerism is nowhere connected to this chapter, nowhere, right? Okay, yes. So law of mass action, right? What is the law of mass action? Let's understand. So firstly, for mass action, you need to understand what is active mass. Okay, what do you mean by active mass, right? So active masses are amount of substance per unit volume participating in a chemical reaction. How much amount of reactant, how much amount of product is participating in a chemical reaction. It is represented by a symbol or formula of the substance in the square bracket. Like if you have A, the concentration or pressure of A, right? Now if you see, according to the state of the substance, whether it's solid, solution, liquid, gas, whatsoever, what is the active mass that you use here? Let's say that. If you talk about a solution, an aqueous solution, you will use molar concentration as the active mass. Molar concentration means you will use molarity here. What is molarity? It is number of moles of solute divided by volume in liter. Okay, this is what you will use in case of solution. When you have gases, then you will use partial pressure. Partial pressure will be in atmospheric or will be in bar, that whatsoever is given in the question. Usually it will be atmospheric. Then for pure solid and pure liquid, it is always a constant, and that's why we say that active masses of pure solid, pure liquid are taken as one. Okay, and this is a very useful thing that we will use in our questions, right? Okay, yes. Yes, Shiva, yes. Yes, Shiva, you are right. Okay, yes. Tell me, pure solid and pure liquid, they will have active masses 1. Solution will be in terms of concentration, that is molarity, and gases will be in terms of pressure, right? Okay. Now let's see law of mass section. The rate of any chemical reaction is proportional to the product of active masses. We are saying the rate of forward direction is equals to, is directly proportional to which thing? It is directly proportional to, let's say there is a reaction that is AA plus BB give rise to CC plus DD. Okay, this is the reaction. Okay. Now, if I say from the law of mass section, the rate of chemical reaction is proportional to the product of active masses of reacting substance with each active state raised to the power of the coefficient. So now let's see, if I want to write rate of forward direction, that is directly proportional to the reactants here, product of active masses of the reacting substances. Reacting substances are this one for the forward direction. This is the reacting substance. So this is A and this is B. A raised to power A and this is B raised to power B, because it is raised to the power the stoichiometry coefficient. Similarly, RB is directly proportional to, for backward direction. This is a backward direction. When you move backward, this is becoming the reacting species. This is the reacting species, I'm saying species, right? In the backward direction, these are the reactants and these are the products, right? Is this the way you see it, right? So this is C raised to power C, D raised to power D, right? So now this will be 1, this will be 2, and here we are going to take the answer we are going to see here. If you write it here, if you raise the proportionality sign here, this will become is equals to Kf and this is equals to Kb. Ma'am, what do you mean by Kf and Kb? Kf and Kb are equilibrium constants of forward and backward direction. Now, what is equilibrium state? That rate of forward and backward has to be same. So, Rf is equals to Rb. Rf is nothing but Kf, A raised to power A, B raised to power B. This is nothing but Kb, C raised to power C, D raised to power D. Now, if you see this here, it will become Kf by Kb. Kf by Kb will become C raised to power C, D raised to power D divided by A raised to power A, B raised to power B, isn't it? Now, can you see what is this Kf by Kb? Now, this is quite important. Very, very good evening, Nikisha. Very good evening. Broken heart. Why your heart is broken? What has happened? So Kf by Kb is nothing but it is Kc. So we can see this from here that Kc, that is the equilibrium, overall equilibrium constant of the reaction, that is equals to product raised to power stoichiometry divided by reactant raised to power stoichiometry. That is the formula for any equilibrium constant. Okay? Right, everybody? Yes, you have Namrata ma'am's class today. Today in the morning, Sher sir took the class. Yes, Sion, very, very good evening. Yes, ma'am, I have issue with physical chemistry part. How do I start learning that backlog, ma'am? How do I start learning? By doing practice with me, right? That's the best thing that you can do, because I'll make every chapter easy for you, so don't worry about that, right? Okay, so this whole derivation that we have done, so we will do this also we have done, right? Let's see the questions here. Okay, this we have done, this already I have taught you law of chemical equilibrium. Okay, this also we have done. Kc is the equilibrium constant in terms of concentration, constant expression. All the concentration are at equilibrium and are expressed. And now this is the important thing. If I say this is Kc, right? Here C, D, A, B, all of these are at equilibrium. At equilibrium. If you put the concentrations, then it will be equilibrium constant. Right? Okay? Right, I think we don't need to have this particular slide here. So let's see a very simple question here. That is, let's see a quite a simple question here. That is, they are saying in the figure shown below, reactant A represented by a square is equilibrium. Reactant is A is represented by a square, that is the reactant. That is the reactant. And B is the product, that is represented by a circle. That is the product. They are asking you equilibrium constant. So equilibrium constant is what? Kc is product by reactant. Product by reactant. So how many product you have? Product is circle. So circle is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it is 12. What is the reactant here? Reactant is 1, 2, 3, 4, 5, 6. It is 6. So it is going to be 2. So D is the correct answer. Quite a very, very simple question. Right? Okay, everybody? Got it? Yes. Right, so that was a easy peasy question. Let's do some more interesting, questions here like this. Okay, let's do some interesting questions like this. Some reaction is given to you, Kc is given to you. If the rate constant of forward reaction is this, rate constant of backward reaction will be what? Now, rate constant means they are telling you equilibrium constant here, right? That is K. They are telling you here. It should be equilibrium constant actually. So Kf by Kb is equals to Kc. This is the formula that we will apply here. So we'll say that Kc is equals to Kf by Kb. They are asking you Kb, that is equals to Kf by Kc. What is Kf? This is a forward direction, mole per mole liter per second. Okay. And this is Kc. So I'll just put this 1.54 divided by 0.50. That is nothing but half. So that is 1.54 multiplied by 2. That is something 3.08. Right? If you put it here, ma'am, okay, this is going to be 3.08. But ma'am, what is the funny thing here? That ma'am, three values are 3.08. So that means you'll have to see the units here. Units of This will be uh, kf has what unit? The units of kf is nothing but it is per mole liter per second. You always don't ever put yourself the units, right? See the units that are written here. Kc units are mole per liter. So this will go here, this will become mole per mole square, this will become liter square, this is per second. So per mole square, liter square per second, that means A is going to be the correct answer here. Right, so answer is A is the correct answer. Right, okay, yes everybody. Let's see. Achha, there is another thing that is KPI, but before that tell me, Sion, that's not a reasoning question. That is not a question from your reasoning part of some government exam that big square also will have to take. Okay? That is just a question, so like interesting question to understand things. Okay? Big circle, no. Right? Sion is going like beyond, ma'am. I'm like thinking, ma'am, out of the box, ma'am. Okay, see this now. Just like you had Kc, but in Kc we were discussing about concentrations, right? In Kp we'll discuss about partial pressures. Okay? Right, everybody? What we are going to discuss here is about partial pressures, right? So instead of writing concentration of C, concentration of D, concentration of A, concentration of B, we are writing partial pressure of product raised to power stoichiometry, partial pressure of reactant raised to power stoichiometry, partial pressure of reactant raised to power, partial pressure of product raised to power stoichiometry divided by partial pressure of reactant raised to power stoichiometry multiplied by partial pressure of reactant raised to power stoichiometry, and that is the answer for Kp. Okay, so there are two kind of equilibrium constants, constant that you have. One is Kp, another is Kc, right? Kc is equilibrium constant in terms of concentration, and this is equilibrium constant in terms of partial pressure. Right? Okay. If you see, the units of Kc and Kp will vary here. Let's see how they are going to vary. Right? Units of Kc is mole per liter and delta N. Delta N is defined the number of moles of product minus number of moles of reactants. Right? And here, in this case, delta N will be gases plus aqueous solution. Don't take, I'll just mention this. This is gas plus aqueous solution. Don't take pure solid or liquid. Why? Because pure solid and liquid, the concentration, the active mass is 1. Okay, let me teach you one example here. Let's say you have CaCO3 give rise to CaO plus CO2. Okay. Now if you see, this is also solid, this is also solid, this is gas. When you want to write the expression of Kc, you will write only concentration of CO2. You will not write the concentration of the solid, because solid is going to be 1. That is why the unit will become mole per liter. You will not add these things here. This is 1 and this is also 1. Similarly, when you write Kp, you add only pressure of CO2. That's why this will not have these solid things. That's why, okay, I'll tell you one more example here, where you have aqueous as well. Okay, let's see one example where you have aqueous as well. Let's take an example. Which example should I take? Wait a minute. Let me see on the front page if we have some example. This example I have taken. These are also gases, gases, gases. Chalo, I'll just take it as A, B. Right now, no example is coming in my mind, so I'll take it as A, B. Okay? See this thing now. When I talk about the example, how we are going to discuss that thing. See, let's say this is A, this is B, give rise to C. This is a gas, this is solid, and this is aqueous. You want to write down the value of Kc here. For Kc, what you will write here? For Kc, you include concentration of aqueous solutions and you include concentration of gases as well. So it will be concentration of C, right, divided by concentration of A. But in sometimes for the gases pressure is given, then you write pressure of A also, right? But here, see, Kp will not be defined. If you define the Kp value here, if you define the Kp value, then you can only take the pressure here. Okay, pressure of only this you can take. Only this will have pressure. These two will not have any pressure. So that's why you can write only 1 by pressure of A. Right? And that is the reason I am telling you that here you will use gases and aqueous solution. Delta Ng will include gases and aqueous solution. Because if you see this solid, I am taking it as 1, I am not including it in the expression of Kc. Then how can I write the number of moles and subtract it? When you will see that this mole per liter will cancel each other. So you will say, let's say this is 2 and this is 1, right? So this will be 2, this will be 1. So delta N will be 2 minus 1 is equals to 1. It will not be 2 minus 2. So we will not include B here, right? B is not included here. Let's say if I want to write the Kp value here, that is pressure of CO2, right? That is the pressure of CO2. Now in this case, if you see, in this case, if you see, this is Kp is equals to pressure of CO2. Now here, what is delta N? That is nothing but 1. Because you have not taken this, you have not included these two. You have only included this. So in the case of Kp, this only means gas. This only means we are talking about gas. Okay. So what is unit of Kc? Mole per liter, delta Ng. And for unit of Kp, it will be atmospheric delta Ng. Tell me guys, this is an important thing. Tell me if that was clear to all of you or not. Right? If you see this question here we are discussing this is gas, this is gas, this is gas. We can definitely define the concentration of a gas as we have defined here. This was gas, but I have defined the concentration of gas. So here, this will be included, this will be included, this will be included. So delta Ng will be 2 minus 4, that is minus 2. That is why unit of Kc will be mole per liter minus 2, unit of Kp will be atmospheric raised to power minus 2. In this case, this is 1, and that is the reason delta Ng will be equals to 1. So unit of Kc will be mole per liter 1, unit of Kp will be atmospheric raised to power 1. Right? Okay. Now let us define the relation of Kp and Kc, which is a very, very important relation from where the questions are directly asked to you in the exam. Direct means very direct questions are asked here, right? Okay. Shiva, thank you. I think you were stalking me, but it's been 10 years, I think, right, that you are talking. So let's see. Instead of going through my Insta profile, you must go through this right now. Okay. So Relation between Kc and Kp. Let's see what is Kc. First, I'll write down the what is Kc, and then I'll write down Kp. Then we will see how to interconvert these two things. So if I say, first I want to define that how concentration and partial pressure are related. Now PV is equals to nRT. P is the pressure, number of moles, volume, temperature, right? You can also write it as P is equals to N by V RT, right? So you can say P is equals to concentration, that let's see, this is CRT. Okay, this is the relation that you have. Now see what we will do. Now let's see what we will do. What is Kp? What is Kc? Kc is equals to, firstly I'll just write Kp. Kp is equals to C raised to power C, D raised to power D. Arre Kp. Pc raised to power C, Pd raised to power D, Pa raised to power A, and Pb raised to power B. Okay, this is for the expression AA plus BB, that expression only. And what is the value of Kc? That is nothing but concentration of C raised to power C, concentration of D raised to power D, concentration of A raised to power A, concentration of B raised to power B. Now, what we will do, okay. Okay, let's see. Let's see. This is the value that you have. Now, on the next page, and this is, I'll just write the what is the reaction, then students will be like, ma'am, what was the reaction actually? Right? See, this is small c raised to power, this is C, and this is small d, and this is D. For this reaction, you have this particular relation. For this reaction, the value of Kp is this, the value of Kc is this, isn't it? Now let's see how do we define, how we understand that what will be the relation here. See one thing here. If I write down Kp is equals to P C raised to power C, P D raised to power D, P A raised to power A, P B raised to power B. Also, pressure is equals to concentration RT. So concentration, I will write it as molarity RT, MRT. Okay, or you can just write it like this, concentration RT. So you can write P of A is A of RT, P of B is B of RT, P of C is C of RT. C of RT means this is concentration. P of D is D of RT. Okay. Now if you see, you put all the values there, then Kp will become what? You will write Kp is equals to, Pc means what you have. What is Pc? Pc means concentration of C, RT, right? And this will be whole raised to power C. This will be concentration of D, RT. This will be whole raised to power D. Divided by, this is divided by concentration of A, RT raised to power A, and this is concentration of B, RT raised to power B. Now if you see this here, what you can do, you can just take the value of Kp is equals to C raised to power C, D raised to power D, this is A raised to power A, and this is B raised to power B, and this will be RT raised to power C plus D minus A plus B. Okay, minus A plus B. Now if you see this here, what we will do, Kp is nothing but this is Kc, this is RT, this is raised to power delta Ng. This is the full-fledged relation that you have. That is very, very important relation, and you will see a lot of questions based on that. Ma'am, here what is R? R is equals to 0.0, because we are talking about pressure and concentration. It is 0.0821. That is also taken as 1 by 12. Okay, in fraction it is also taken as 1 by 12. What is T? T is the temperature in Kelvin. And what is delta Ng? Delta Ng is product minus reactant, moles, gaseous moles of gaseous moles product minus reactant. Okay, you do product minus reactant for the gaseous moles, right? Okay, yes. Okay, now that is the thing, number of gaseous moles by gaseous, and this means if I am saying gaseous means gaseous. Now if you say, ma'am, but why you have written gaseous? Bacha, here I have defined na Kp is only applicable for, I'll just write this here as well. We have Kp here. Kp is only for gases. Here all of them should be gases. Kc is applicable for aqueous solution and gases. Concentration you can find out for aqueous solution as well and gases as well, but Kp only you can find it for gases. That is why in this particular equation that we have written, this is only for gases. These all are gases here. That's why whenever you see this relation, write down this thing that it is for only gases here. Let's see the questions now. JEE 2023 question. Let's see that, everybody. JEE 2023 question. Let's see that. For the reaction, that is this one, Kp is given and 1 atmospheric, this is the temperature, this is the pressure, Kp is given, Kc for the same reaction is what? So guys, Kp is equals to Kc RT raised to power delta Ng. What is delta Ng here? Gaseous product is 1, reactant is 1 plus this, that is 1.5, and that will be 0.5, that is nothing but half. Actually it is minus half. This will be minus half. So you can write this here, Kc is given, Kp is equals to Kc. Kc is what? Achha, Kc you have to find out. Kp is given. Okay. So you will say Kc is equals to Kp RT raised to power minus delta Ng. So Kp is what? This is 2 into 10 raised to power 12. And R means what? R is 1 by 12. Temperature is given to be 27, means 300 is the temperature. Minus of minus half means this is nothing but half. Right? Now just solve this particular equation and you will get your answer for Kc. Tell me, everybody, is that clear? Is that clear? Why I am putting R is equals to 1 by 12 to make your calculations easy. Okay, I am putting it as 1 by 12. You solve 1 by 12, that is 0.0821 only. Okay, and why we have put, ma'am, 0.0821? Whenever things are in liter, atmospheric, we are talking about concentration, pressure, then we will take R is equals to 0.0821. Yes. Okay, I'll check your time in free time, right? Acha, tell me, right? That you will do, solve your answer and you will get your answer. Okay? Right, everybody? Next question is 2019 question, that is, in which one of the following equilibrium Kp is not equals to Kc? That means where delta Ng is not equals to 0. You have to find that. If delta Ng is 0, then Kp is equals to Kc RT raised to power 0. That means Kp will be equals to Kc. So we have to see where delta Ng is not equals to 0. So this delta Ng here, this is 2 minus, this is solid, so it will not be included. This is 2 minus 1, that is 1. Answer will be A. Right? So here it is delta Ng, product is 2, reactant is 2. So it is 0. Here delta Ng, gas, so it is 2. This is gas, that is also 2. So it is 0. Here delta Ng, this is product is 2. This is also 2. So it is going to be 0. So answer again will be A is the correct answer here. Right, everybody? Okay. Tell me everyone, is that clear? Next question, JEE 2020. See how in seconds we are solving this question. So the KP-KC relation questions are very important and you can just solve this within seconds, right? Okay, especially if calculations are not involved, then to in literally 5 to 10 seconds you can solve this, right? Okay, let's see. Consider the reaction, the temperature at which Kc is equal to this, Kp is this. Okay, now they are saying calculate the temperature now, right? Demands are changing. Kp is equals to Kc RT raised to power delta Ng. What is the value of delta Ng here? That is 0. No, it's not 0. It's 2 minus 1, that is 1. Okay? I was like, then how will I calculate? So, Kp is equals to Kc RT raised to power 1. Ma'am, then Kp is equals to Kc RT, definitely, right? Now, when you see this thing here, next is, ma'am, now what should we do? Ma'am, we have to calculate temperature. Kp is given, that is 600. I'll take 0.1 also. Kc is given 20.4. R is given 1 by 12. Temperature you have to solve. Then temperature will be 600.1 multiplied by 12 divided by 20.4, and this will be your answer here. Solve this and you will get your answer in Kelvins. Ma'am, why we will get our answer in Kelvin? Because this R is given in per Kelvin. That's why answer will be in Kelvin only. And they have asked also in Kelvin. So you can say 1600, 600, this is 12, this is 20, this is 6. This is approximately 636. 360 something it will be, right? Okay. So answer is 354, right? So answer is coming out to be 354 is the correct answer here. Right, everybody? Let's see if you can do this question, right? Or shall I give you this for homework? Tell me. Will you do that? Right? Will you do that? Yes, Shiva, Beno. Let's see how many likes you have given to this lecture. Let's see that. Okay, let's do this, everybody. At 700 Kelvin, the equilibrium constant Kp for the reaction is 2SO2. This is the reaction, that is 2SO3 give rise to 2SO2 plus O2. All of them are gases here. So they have given the Kp value. Kp is given to be 1.8 into 10 raised to power minus 3 atmospheric. See, from the Kp value only it is clear that delta Ng is 1. But still we will do that. Value of Kc for the above reaction. See, delta Ng is what? product minus reactant. Product is 3, reactant is 2, it is 1. I am taking gaseous products. Okay, gaseous product, right? Okay, yes. Okay, Shiva, yes. Now if you see Kp is equals to Kc raised to power Rt raised to power delta Ng, that is 1 itself. Kc will be what? Kc is Kp Rt raised to power minus delta Ng. So Kc will be, what is Kp? Kp is given 1.8 into 10 raised to power minus 3. R is 1 by 12. Temperature is given to be what? 700. This is minus of 1. Right? That will become 12 by 700. So I can write it as 12 by 700. Right? Okay? Because you know this will become Kp Rt minus 1. So that will become Kp by Rt. R is 1 by 12. This is this. Solve this and you will get your answer. Right, everybody? Ma'am, who's gonna teach us chemical kinetics today? This person standing here. After my dinner, I'll teach you chemical kinetics. Okay? Yes. Don't be like, ma'am, you are on YouTube, then who will teach us in the Sigma batch? I'll teach you. Don't worry. Right? Okay? Yes. Now let's see. Next, that is factors affecting equilibrium constant. Factors affecting equilibrium constant. See. So let's see one by one. First is equilibrium constant does not depend upon concentration. It does not depend upon concentration of various reactants and products. Presence does not depend upon concentration of various reactants and products. Presence of catalyst, direction from which equilibrium is reached. Wait. Equilibrium constant. So we are saying that equilibrium constant will not depend upon the concentration of reactant and products, right? And the presence of catalyst is there or not, right? Or the direction from which the equilibrium is reached. It will not depend upon all these cases, right? And here we are talking about Kc, right? Equilibrium constant is dependent upon which things? Then it depends only on the temperature. Now this is a very important question. Usually students have this misconception that Kc is equals to product by reactant concentration. So it depends upon concentration. But the concentration, if you see, are also cancelled with each other. So equilibrium constant will not depend upon the initial concentration or the catalyst or the direction from which it is reached. It depends only on the temperature, right? Like, let's see how it depends upon the temperature. This all I'll teach you with Clausius-Caprion equation. This is a ultra pro level important equation, right? If you want, like, ma'am, I want to have good hold over chemical equilibrium, over ionic equilibrium, this is the equation. You should know this equation like throughout. This is log of K2 by K1 is equals to delta H 2.303 R. This will be T2 minus T1 by T1 into T2. Okay, or I'll just change this thing here, right? I'll just change this thing here. Instead of writing 1 by T1 and this, write it like this. Write it like this. It will be more easy to understand why it is different for endo and exothermic reactions. Okay, let's understand. For endothermic, what happens? For exothermic, what happens? Let's understand that. It is here only, so I'll just do this here only. Endothermic, exothermic, let's see guys what happens here in this equation. Firstly, I'll talk about endothermic reaction. right? Let's understand in endothermic reaction what happens here. See this one thing here. In endothermic reaction, what is happening? In endothermic, delta H is positive here. Delta H is positive in endothermic. Always remember, if I say temperature is increasing, that means T2 is greater than T1, right? That means for an endothermic reaction, now here I'll define it for two things, okay? I'll define it for endo and exo. This is for endo. Endothermic means delta H is positive. And for endothermic, delta H is positive, right? Yes. Two lectures, right? Positive. This is positive. This is positive. Because if I say T1 is greater than T2, that means T2 minus T1 is positive, right? That means, can I say T2 minus T1 is positive? If this is positive, that means this full equation here will be positive. That means log of K2 by K1 will be positive. Now log of anything is positive if that anything is greater than 1, that means K2 is greater than K1, and this is what we have written here, that in case of endothermic K2 is greater than K1, and that is why we know that T2 is also greater than T1, so temperature is directly proportional to K in this case, right? In this case, you can just directly write here, temperature is directly proportional to Kc. As temperature increases, Kc also increases, right? Next is, if I say it is an exothermic process. Okay, everybody tell me, for an exothermic process, what is the value of delta H? What is the value of delta H? In exothermic process, what is the value of delta H? That is negative. If I say this is negative, this one is positive, because temperature is obviously increasing. Here as well, I am talking about when it is increasing. Okay. So this is negative, this is positive. That means this overall equation, that you see here will be negative. If this overall situation here is negative, that means, can I say log of K2 by K1 is negative? Don't spam, right? If log of anything is negative, that means that anything is obviously less than 1. That means this is less than 1. So I'll just write it here. That means K2 by K1 is less than 1. That means K2 is less than K1. That means as temperature increases, K decreases, right? Here it was in opposite. Here K2 was greater than K1. So here as temperature increases, K was increasing, right? So that's why we are writing that for an exothermic reaction, temperature is inversely proportional to Kc, right? This is important. That's how it is dependent upon the type of reaction you have. That's how Kc is dependent upon the constant. But I'll have to block you if I see more of this. If you have any question, then ask. Why are you spamming it? I can see that you're typing one question, right? That's what I told. Pressure, concentration, catalyst, all of this will not affect, but temperature change will affect the equilibrium constant value, right? Temperature change is going to affect it. If you see delta H is 0, there is no heat evolved or absorbed. If this is 0, this is 0. If this is 0, that means K2 is equals to K1. If K2 is equals to K1, there is no, it has temperature, has no effect. So on those reactions where delta H is 0, then temperature, then Kc will be temperature independent. But when it is exo or endothermic, then it will be temperature dependent. Right? Okay. Let's see the next thing here, that is factors affecting equilibrium constant, more of the factors, that is the stoichiometry of the reaction. Right, everybody? Let's do this. At constant averaging, constant Kc is this. A plus B, if take 2 moles. This is the proper question you are giving me. Shayan, proper question is it? So you can do one thing, you post it on my Telegram group, then I'll solve it. Right? Okay? Yes. Now equilibrium constant depends upon the stoichiometry. Now it depends upon the stoichiometry of the reaction. Let's see how. If you see, you have, now I'll see how it changes with the stoichiometry. If we have two reactions that we are adding, you have reaction number this one, this is reaction 1 and this is reaction 2, right? You are adding these two reactions, then their equilibrium constants will be multiplied. Ma'am, why they will be multiplied? If you see here, K1 is equals to product by reactant, here K2 is equals to product by reactant, that is D by B. When you multiply K1 into K2, you will have this CD and AB, which is nothing but this is equilibrium constant when you add these two reactions, that is product by reactant concentration. So that means when you add two reactions, their equilibrium constants will be multiplied with each other, that is the new equilibrium constant. And this is one of the simplest concept that you have for your JEE Mains. Actually, this is the simplest concept that you have, right? And if they ask you questions from here and still you are not able to do it, then it will be your mistake. Thank you. Okay, Shiva. Definitely, right? Then if I say if the equation is reversed, now you have this equation, right? And you have this equation, both are reversed. If you see the Kc of both, here Kc is C, product by reactant, here Kc dash, new Kc when the reaction is reversed is product, that is A, B, C, D is the reactant, so it is this. If you see, aren't they inverse of each other? So when you reverse a reaction, their equilibrium constants are inverse of each other, right? When you add, their equilibrium constants will be multiplied. When you reverse the reaction, their equilibrium constants will be inverse of each other. Then if I say you multiply it with some factor, right? When you multiply it with some number, right? Now for this particular equation, the equilibrium constant is product by reactant, that is written over here. If you multiply it by n, that is this reaction, it is C raised to power n, D raised to power n, A raised to power n, B raised to power n. You take all of this will be raised to power n, that is nothing but new equilibrium constant is old equilibrium constant raised to power the number that you have multiplied here. Such a simple thing. So what we have discussed, when you add, both will be multiplied. When you reverse, it will be inverse. When you multiply it with some number, that number will be in the power. Okay? Tell me everybody. Right? Next is, and we'll do questions based on that as well. Right? Let's just see the last point, then we'll do question based on that as well. So here it is, equilibrium constant also depends on the unit in which it is expressed. The unit in which it is expressed, right? How? If the unit of the concentration of the reactant and product are changed, then there is change in the magnitude of K. That means if you are representing Kc in atmosphere, then you change it to bar because the units are changing. When you will multiply it with something to convert it into bar. That's why the value of Kc will also change. Okay. Now let's see the questions based on this thing, and you will see latest questions, and they are very simple questions. Okay, they are quite simple. Ma'am, we multiply or divide, k will change. Yes, you multiply or you divide, k will change. Your inverse, k will change. You add two equations, k will change. You subtract two equations, k will change. Okay, so in the crux, I'll just write it here. When you add two equations, it will be multiplied. When you subtract two equations, it will be divided. When you multiply it with a factor n, it will be in the inverse. When you divide it with a factor, it will be also in the inverse. Okay? When you inverse the reaction, reverse the reaction, it will be 1 by k. Okay? I'll just write here only. When you reverse the reaction, it will be 1 by k. Okay. Yes, students. Right? Done, done. Right? Let's see this. JEE 2023 concept. Let's see. Concept of JEE 2023. That is, you have an equation where k1 is given, k2 is given, k3 is given. For this equation, you have to answer. You will see this is quite similar to Hess's law. If you see there also some 2-3 equations were given, by multiplying, adding, you have to find out the last equation that they were asking. Same kind of thing we are doing here, right? Okay, yes. So organic lecture, I know you guys are waiting for aldehyde, ketones, amines, biomolecules. I'll do that, but I'll do that in one shot or maybe in 2 parts. Okay, so it will be long lectures and we are planning for that, right? And don't worry, it is soon, like within 10-15 days we'll cover that, right? Don't worry about that, that is in my mind. Okay, based on the above equilibria, the equilibrium constant of the reaction, this is what. Now, how do you answer that? How these are related to this one? If you see NH3, you need to have on the reactant side, so this will be inversed. This will be inversed. This will be inversed. So this will become K1 dash, that is 1 by 4 into 10 raised to power 5. Then this 5 by 2, okay, 2NO you have here, okay, that will not be inversed. 2NO is not anywhere else. And then you have 3H2O, that means this will be multiplied by 3. Okay, so this will be, it will be multiplied by 3 means nu will be K3 raised to power 3. That is 1 into 10 raised to power minus 3. Here also you can write 1 by K1. Okay, here also you can write that K3 dash will be K3 raised to power 3. Then you add these 3 equations, right? Then you will have this one. You can also do that. I just saw this is 2NH3. It is on the product side. I'll have to inverse it. 2NO is there. Here also 2NO. That means you don't have to multiply, divide or inverse anything. You don't have to do. Then 3H2O means this has to be multiplied by 3. Okay, only then this will become 5 by 2. Oh, sorry, this will become 3 by 2. And 3 by 2 plus 1 is nothing but it is 5 by 2. And here they have asked you 5 by 2. Right? Rest of the things will be cancelled here. Like if you multiply this by 3, this will become 3, this will become 3 by 2, this will become 3. Then this 3 and this will be cancelled. N2 will be cancelled here. How N2 will be cancelled? Let me teach you that as well. Because this will become 2NH3 give rise to N2 plus 3H2. When you add all of them, on adding, things that are on the opposite sides are cancelled, no? So this and this will be cancelled. This and this will be cancelled. So we just need to add K1 dash, K2 and this. So it will become new K is equals to K1 dash multiplied by K2 multiplied by K3 dash. K1 dash is 1 by K, K2 is K2 only, and K3 dash is nothing but that is K3 cube. So it will be K2 into K3 cube divided by K1. That is the new K that you have. So you can say Kc is equals to this. Okay. Now you just have to put all the values and get the answer. Right? Okay. So that is K is equals to K2 into K3 cube by K1. Put all the values and you will get your answer. Right? Next question is this one, where again we are doing same. See, it's very simple questions you have here. Which of the following three reactions A, B, C equilibrium constants are given? Which of the following relations are correct here? So in the end, you should have CH4 that is here. You need to add these two equations, then it will become 2 water. You need to add these two equations, this will become CO2. CO will be cancelled here. This will become CO2 and this will become 3 plus 1, 2. So you can say K3 is equals to addition of both, because this, if I say this is first, this is second and this is third, then third is equals to 1 plus 2. That means K3 is equals to K1 into K2. So answer will be B is the correct answer here. Tell me everybody if that is clear to all of you or not. Yes, students? Is that clear to all of you or not? Right? Yes. Is that clear to all of you or not, everyone? Do let me know in the chat box. Right? Yes. So, next is this question, and let me see how many of you are able to answer this. Let's see how many of you are able to answer this question. Let's see that here. And also hit the like button, guys. So much energies we put in, like, teaching you things in detail so that no concept goes unattended, right? So equilibrium constant of the followings are given to you, 1, 2, 3, and equilibrium constant of this reaction we are asking. I think that is same as first one that we have discussed, right? It is same as the first one that we have discussed. Yes, it was K1, it was K2 into K3 cube by K1. This is the same thing that we have discussed there, right? Same thing, that this and this question is same, guys. You see, it's the same one. Okay, so that is there, right? Okay, any problem in solving these kind of questions, do let me know in the chat box. Any problem you have over there, do let me know in the chat box, right? So that we can do the next thing here, right? Chayan, you can just put in your question in the comment section and then I'll definitely reply, okay? Yes. So here you have applications of equilibrium constant. What is the application of equilibrium constant? So we'll do few questions here, but more of this thing we'll do in the next class, right? Because next class we'll do Lee Chatelier principle and some of the important things, but today we'll do like QC, reaction quotient, right? These things we'll do today, but next class the dissociation constant, how degree of dissociation is related, all of those numericals we'll do in the next class. Okay, that is very important and very confusing as well, right? So applications of equilibrium constant, what is there? Predict the extent of reaction. First thing is to predict the extent, how much the reaction can go forward or backward, the direction of the reaction, is it going in forward or backward direction, and calculate the equilibrium concentrations of the reaction. So in today's class we'll do these two things, okay, and third we will do in the next class, right? So first is predict the extent of reaction on the basis of the magnitude. Let's see how. So if you have this reaction and if I tell you that your equilibrium constant is greater than 10 raised to power 3, then in that case you will say that it will move in the forward direction. This will follow forward direction, right? And that is the reason this will be product favorable. More concentration will be there for the product. It is a very good reaction that is favoring the product, right? So product concentration will be more. If I say it is less than 10 raised per minus 3, so it is reactant, it is so slow that this is reactant favorable, okay? It is reactant favorable reaction. It is more favored. It is such a slow reaction that it is reactant favorable, right? But if it is between 10 raised per minus 3 and 3, then we can say appreciable concentration of reactant and products are there, right? So if I see it is 10 raised to power 8, then means it is greater than 10 raised power 3, so it will be product favorable, right? Okay, understood? So it was easy. Then predict the extent of reaction. One more thing you have here, that is the same, this way of writing it is different. If it is 1, that means you can say not 1. If it is in between 10 raised power minus 3 and 3, then we can say it is both product and reactant favorable. If it is less than 10 raised power minus 3, then it will be reactant favorable. Reaction hardly proceed, it will not proceed, it is very slow, right? But if it is very great, it is greater than 10 raised to power 3, then the reaction almost is towards the completion, okay? So if it is between 10 raised to power minus 3 to 10 raised to power 3, we can say it is reactant and products both are there. If it is less than 10 raised to power minus 3, it is not even moving. If it is greater than 10 raised to power 3, then we can say it is like very fast. It is almost towards the completion. That tells us the extent of the reaction, how much reaction is going on. Then we say the prediction of direction of the reaction, whether it will be forward or it will be backward. This is based on a new quantity that is called as reaction quotient, that is QC, right? So, ma'am, what is this QC? Let's see that. See, at each point in the reaction, let's say this is the reaction and this is the point of equilibrium. So apart from equilibrium, at each point, when you put the concentration value, that is QC. So the formula of QC and KC is same. QC is also C raised to power C, D raised to power D, divided by A raised to power A, and this is B raised to power B. The formula is not different. If you put equilibrium concentration, that is equilibrium constant. If you put any other concentration apart from equilibrium, that is called QC. And QC is the thing that you use in Nernst equation, right? In class 12, you will use that. And those who are in class 12, they already know what I am talking about, right? So, at each point you have, we can write the ratio of concentration having expression same as equilibrium constant. When you write any concentration apart from equilibrium, that is reaction quotient, and it helps in predicting the direction of reaction. Let's see, and it is variable, right? This is equilibrium. If you see, if you put the concentration here, 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 it will change, and that's why it is a variable quantity, right? Okay. Now see, QC is same. The formula is same as reaction, same as equilibrium constant. The difference is at any time during the reaction, you will put the concentration, but it should not be equilibrium concentration. If you see, this is the equilibrium point. If I say reaction quotient, if you increase the reaction quotient, increase, at one point it reaches the equilibrium constant, right? At one point, QC only becomes KC when the concentrations are at equilibrium. That means we can say, how does it tell whether the reaction is forward or backward? If I say QC is less or equal or greater, according to that it will tell. Let's see how. See students, if I say this is, let's fix one thing. Let's say this is Kc. This is fixed for a reaction. I'll not change this. This is fixed for a reaction. This is Qc. If Qc is less and this is increasing, okay, this is increasing. If Qc is less, then to make these two things equal, it will have to move forward. See, equilibrium is the stable position. Everyone wants to be in their stable position. You also want to be in your stable position. I also want to be in my stable position. So QC also wants to be at equilibrium. So this is KC, which is fixed. A stable position is fixed, right? Now QC, which is not equals to KC, wants to become equal to KC because it wants to be in a stable situation. So it will move in the forward direction. It is moving in the forward direction. Can you see it is moving in the forward direction, right? So when QC is less than KC, then it will move in the forward direction to make it equal. When QC is equal to KC, they are already at equilibrium, right? But, so they will not move. But if this is KC and this is QC, which is greater, now to be in the stable situation, QC has to come backward. So this will be backward direction. So when QC is greater than KC, it is the backward direction. Backward, and this is the forward. Okay, it is already written there. This will go forward, this will go backward. In the end, what all you have to do is, you have to equate this point. This should be there. QC should decrease, so it is backward. QC should increase, so it is forward. This is what I have written, Louis, here. This is what I have written here. If Kc is very small, then the reaction is very slow. This is the extent of reaction. Whether it's very slow or it's very fast. If Kc is very less, then it is very slow. If Kc is extremely large, above than 10 raised by 3, it is very fast. Okay? And here, based on QC and Kc, we have seen whether it's a forward reaction or it's a backward reaction. Okay, let's see this thing now. The reaction quotient for the reaction is given is this. The reaction will proceed from right to left. In what case? Right to left means what? Right to left means, this is right, no? This is the reaction, this is the left side, this is the right side. Right to left means backward. When it will go in the backward direction, when QC is greater than KC. If QC is greater than KC, it will move in the backward direction. Okay? So answer will be C is the correct answer here. Okay. Yes, everybody. Which reaction will move in the backward direction? The one where QC is greater than KC. Right? One where QC is greater than KC. Right? Okay. Yes, everybody, tell me. Is that clear? Is that clear, everyone? So, now rest of the things we'll do in the next class, okay? Yes, these things we'll do in the next class because I want you to compare it with the degree of dissociation, everything as well, right? So that's it for today, guys. Now I'll see you all in the next class. That is tomorrow at 8 p.m. I'll see you all at 8 p.m. And tomorrow also there is one more thing, right? There is one more thing. And you know what is that? How many of you know what is that? Yes. How many of you, what is that great thing that is going to happen tomorrow? And how many of you are waiting for that? Let's see. So guys, if you see this over here, right? First thing is, this is your friend Ved, and this is totally free of cost. Click on Ask Doubts from Ved. Click on this particular link. You will get the PDF of this session on this particular link only. And also, anything, any doubt, you're watching this on the recorded version, any doubt you have, right? Then you can ask Ved about your doubts, and this will be cleared, right? So any question you have, you ask the Ved regarding this particular lecture, and that will be done, right? So PDF and your doubts, everything will be taken on this link, right? And now on this channel, if you see, go and click on this channel, go to the live section. Tomorrow something really great is happening, right? First thing is, in the morning, right? What is the time? Because of you, your Diksha ma'am. I am like, I sleep at 2 a.m. guys, right? But I'll wake up for you at 6 a.m. only for you. I don't know for how, like, it's been such a long time. I have not wake up at 6 a.m. But I'll wake up for you. Not actually 6, I'll wake up at 5:30 a.m. because I'll be having your session at 6 a.m. tomorrow. So click on this session and hit the like button here as well, everybody. Hit the like button here as well, right? For your Diksha ma'am itself. See, 1 like is there, and Diksha ma'am is coming at 6 a.m., right? So spread the word, share it with your friends. Even if you have your school tomorrow, 6 to 6:40, 6:45, 6:50, maximum class will be there. And we are going to do some very, very important questions from coordination chemistry, right? I have picked these questions specially for you. So everybody do join in the class tomorrow at 6 a.m. And also at 6 p.m. what is happening, ma'am? At 6 p.m. what is happening? Let's see over here. At 6 p.m. what is happening? You will see this over here. Click on this link. See, 6 a.m., 6 p.m. some really interesting things are coming. So over here you have a Chatelier rank booster test series, right? Shreyas sir is going to tell you everything in detail about this series, that how it is important, part syllabus, full syllabus, how many tests will be there, right? And will there be any, like, if you say, ma'am, full syllabus tests are there, will there be full 11th class test, full 12th class test, right? And will it be based on your previous year question, or will there be non-PYQs as well? So everything will be there on this session, and Shreyas sir is going to tell you about this. Your own Capto is going to tell you about this. So hit the like button here. This will be at 6 p.m. and I'll see you all at 6 a.m. tomorrow in the morning. See you all. Till then, bye-bye everybody. See you all. Bye-bye. Take care. Yes. Yes. Definitely, Shiva. I'll definitely see that. Now, I'll see you all at tomorrow in the morning at 6 a.m. on this channel itself. See you all tomorrow. Bye-bye. And coordination chemistry, top interesting, most important questions of coordination chemistry. Till then, bye-bye.